Today we are going to study the second part of the chapter 4, and we will discuss the wave phenomena, energy of waves. We will focus on intensity concept and the intensity of the sound. Also, we are going to study the sounds from moving sources, which is the Doppler effect. Also, remember you had to complete the pendulum mass and angle lab, you need to complete and submit online, and the same thing you had to do with homework number 5. Here I just include the homework number 5 if you want to start working, but these two, the lab and the homework 5, is the assignments you had to complete for this week. Let's start with the wave phenomena. There are some phenomena or behaviors that can be observed in any time of wave, and these phenomena include the refraction, reflection, diffraction, interference, and resonance. These phenomena occur because of the interaction of the wave with the surrounding. This is why all these phenomena occur. Then we will discuss first the refraction and the reflection phenomena. The refraction occurs when the wave travels from one medium to another medium, for example, air to water. Also, the refraction can happen when the wave moves in the same medium, but the conditions of the medium change. For example, if the wave is traveling air, but the temperature of the air change, for example, from 68 Fahrenheit to 20 Fahrenheit, then the refraction also can occur. Then what happens in the refraction is, because the wave has different velocity depend on the medium, then the wave change in direction when the wave passes from one medium to another medium. Also can change the direction when change from one condition to another condition in the same medium. Then what happens is the wave is bending. Then we can associate maybe the easy way to remember what is the refraction. The refraction occurs because of the bending of a wave. This is the bending of a wave. The second one is the reflection, and this happens when the reflection happens when the wave hits a surface or an object and then bounces off. Then the easy way to remember the reflection, we can associate the reflection with the bounces off. As this is the refraction, what happened with the refraction? The wave is bending. What happened in the refraction? The wave bounces off. As that is I want you to remember. And we can see here in this case, the wave is the visible light. This is the light. Then what happened is the light is traveling first in air and then is traveling in water. And what happened? The speed of the light changes because we have it's traveling in different medium as air, water. And this is why we can see this effect. We can see how it looks like the pencil is broken. In the second example is again the wave is the light, and what happened is the light hit this surface and then reflect. Yes, this reflect. And this is why we can see this effect. This is the reflection. In case of the sound, the reflection is called echo. Yes, it's called echo. And most of the examples I will just here I use the light because it's easier to see, to understand these two phenomena. But in this presentation, we will focus on the wave of the sound, sounds wave. We will focus on sounds wave. Then this is one example where the refraction of sound occur. Remember, refraction is bending of a wave. This is the bending of a wave. And what happens is why the question here is, why can you hear sounds better at night? And the reason is probably because it's quiet, but also this happen because of refraction of sound. And what happened during the day is, because of the sunlight, the surface of Earth is warm, and the upper part, in the upper part, the air is cold. Then what happened is, remember, the speed of the sound depend on the temperature of the air. Then warm, the speed of the sound is high, and in low temperature the speed of the light is low. Then what happened, because of the difference in the speed of the sound wave, the sound wave bending upward, is bending like that. But at night is the opposite. We don't have some sunlight at night. Then what happened is, the surface of air is cold and the upper part is warm. Then what happened is, in this case, we had lower speed, yes, for the sound, higher speed, then this bending downward, as the sound wave bending downward. And this is why we can hear the sounds better at night. This is the example, the reflection, how the reflection occurred in sound wave. Then when the sound, this is the original sound, the red one, when the sounds is traveling and then hit the surface, then that is reflect, that sound wave reflect. Means is the sound wave bounces off, yes, and then it's traveling in opposite direction. What happens is, the reflected sounds arrive after 0.1 seconds. Then the human ear can distinguish the reflected sounds from the original sound. Then if the time between these two waves, between the original sound and the reflected sound, or the echo, that is 0.1 seconds, then we can distinguish these two different ways. We can distinguish, and this phenomenon is called echo. Then there are some species, some animals, that they use echolocations to hum. This is a case of the bat and the dolphins, and they are designed to emit some sounds. Then they receive the echo, and they know exactly where is the prey, as they can know the distance, as they can do the calculations, as they are designed for do that. We are not designed we cannot do that, as we cannot do that. But the bat and the dolphins, they use the echo, yes, to know what is the distance, where the prey is. Now let's do some example here. Then we say before, the human ear can distinguish a reflected sound pulse from the original sound pulse if 0.10 seconds or more elapses between the two sounds. Yes. Then we know the time here. Let me write here the time equals to 0.10 seconds. Then we want to know what is the minimum distance. This is the minimum distance to a reflecting surface from which we can hear echo if the speed of the sound is 343 meters per second. Then we know the speed of the sound in this case is 343 meters per second, and we want to know the minimum distance. We don't know that. Then what happened is, let's see, we can write here. Here is the source of sound, yes, and this emits some sound. This is a wave sound. Here is the surface. It's hit the surface. Then what happened is this is reflected. Yes, it bounces off. Then we can see this is the echo. Then the time the original wave traveled from here, the time elapses between the original sounds is emit. Yes, in this point, travel, hit this one, and then the echo is traveling in opposite direction, equals to 0.10 seconds. Then it's traveling this distance, yes, 0.10 corresponds to this distance plus this distance. Yes. This 0.10 corresponds to all this distance plus this distance. But we want to know the minimum distance. Yes, the minimum distance is from this point to this point. But this time corresponds to twice of the minimum distance. Yes, the time 0.10 seconds corresponds to twice the minimum distance. Then what we can do is we can calculate first the distance and then divide by 2 to get the minimum distance. Let's first calculate the distance. Yes, the distance the wave and the echo travel in 0.10 seconds. Remember, this is the equation because the sounds travel at constant velocity, then this is the equation we need to use. Yes, this is the only equation we need to apply if the velocity is constant. Then let's calculate first, and we need to calculate the distance. The distance is traveling in 10 seconds. Then velocity equals distance over time. Let's solve for the distance, and we know this is usually in the books like that. It's the same thing. Then distance equals to velocity times time. Then distance equal, we don't have problem with the units. The units are consistent, and just multiply 343 meters per second multiply by 0.10 seconds. And the seconds cancel out, and the final units are meter, which are the units we expected. Then 343 times 0.10 is we just because we had here 2 significant digits, and if you multiply you will get this one, but just you will write just with 2 significant digits. Then but this, we know this is not the answer because this is this distance. Yes, all this, and we want just the minimum distance from this point to this point. And to calculate the minimum distance, what we had to do is just divide the distance by 2. Then the minimum distance equals to meters divided by 2. Then the minimum distance 17 meters. Then just because I know you are familiar with feet, this is equals to 56 feet. Okay? This is the minimum distance we need to is the minimum distance in which we can distinguish the original sound from the echo. The next phenomenon we want to discuss is the diffraction. And the diffraction, let's think in one situation. There is someone is playing here music, yes, and we are sitting here, but we had some large post in front of us. Then even if we cannot see the person is playing the music, we can hear that music, yes. And the reason is the sounds can go around the edges or can go around the obstacles, yes. And this is why, yes, this is the sounds can go around the obstacles, and this is why we can hear the music. And in this case, for example, if there is a radio here, yes, and there is a student is walking in this corridor, still she can hear the music, yes, and the reason is these sounds can go around of these edges, yes, can go around of these edges, and the students can hear the music. Also, the diffraction occur when the sounds can pass for small openings, yes, small openings. For example, if someone is not in this room but is outside, and the window is open or the door is some door is open, still we can listen the music, yes. And the reason is the sound is diffract, is passed through this small can pass through the opening, yes, can pass through the opening. And this opening add as a new source of sound, yes. This add as new, it's like if you had new source of sound here. Then just to summarize, the diffraction occurs when the sound is traveling, and if there is some obstacles, that sounds can go around the obstacles. And if there is some small openings, then the sounds can pass through that openings, and then it's like if we're the sounds you will have here as a new source of sound. And maybe the words we can remember here is then in case of the diffractions is the sounds can go around the edges of obstacles and can pass a small opening. The next phenomenon that I want to discuss is the interference, and this occurs when two traveling waves meet. As that happens if we had two waves and they meet, then there is two ways they can interfere. Then they can interfere constructive or in destructive way. And what happens with these two waves interfere with each other, they produce a new disturbance, a new wave. Yes, they produce a new wave. Then what happens with when the interference is constructive? And this occurs when two equal and in phase waves meet. Yes, in phase means the crest coincide with the crest and the throat with the throat. Yes, this is in phase. And what this happen is if they interfere, we add these two waves, we will get a new wave with the double of the amplitude. Yes, here we had the amplitude is 8, 8, then the amplitude here will be 2, 8. Yes, will be 2, 8. And in this case, crest and throat reinforced. Now, what happened in case of the destructive interference? This occurs when two equal but out of phase waves meet. In this case, the crest and the throat coincide. And what happened is, if these two waves meet, they will cancel out. Yes, and crest and throat will be canceled. Yes, this is happening. Another important thing, this phenomenon happens just when the waves meet. After the waves pass, then they will return, and after the interference happen, then they will return to the original amplitude. One thing we can discuss also here is the standing waves, or and how these standing waves happen in vibrating strings. And the standing waves happen when the strings are stretched between two fixed ends. And this, for one example, this happens is the guitar, as the end of the strings are fixed. Then what happens when the end of the strings are fixed and the string start vibrating? Then there is one wave that is travel. This is the original wave. When this wave hit one of the ends, one of the fixed end, is going to reflect as in the opposite direction. Then what happened? The combination of the original wave and the reflection will be create patterns. That patterns are the knot and anti-knot. Yes, it's the knot and anti-knot, something like that. Then the knots are places of the destructive interference. Yes, and it's like in this case. These are the knots. Yes, where the destructive interference happen, and this is the anti-knot. In this video, we will see how the patterns of the knot and anti-knot depend on the frequency, the vibration frequency of the strings. And let's play the video. We can see we had the fixed ends, yes, and how this pattern of anti-knot and knot change depend on the frequency of vibration of the string. And one of the application of this phenomena is in music. And in music, for example, the lowest frequency possible is called the fundamental frequency. It's just we had one anti-knot. Yes, and the other frequencies are called the overtones. Yes, this frequency, we had 2 antinobs, 3 antinobs correspond to the overtone frequencies. And in music, they combine all these different, for example, in case of the guitar, they combine all these different frequencies of the sound to get a characteristic sound quality. Means they can do music. Yes, they can do music. The other phenomenon we want to discuss today is the resonance. And first, we need to introduce this concept. Is first, all elastic objects of elastic materials has a natural frequency of vibration. This natural frequency of vibration depends on the material and the shape of the object. Yes, is the natural frequency of vibration. What happens is when this natural frequency of this object matches with any external frequency. Yes, for example, if the natural frequency is 200 hertz, and this matches with something that is vibrated at 200 hertz, then the sound wave is transferred efficiently because they had the same frequency. This phenomenon is called the resonance. And the natural frequency of the object is called the resonant frequency. Maybe you remember in the movies when the singer shatters a crystal water glass, yes, by singing a single note, yes. But however, the other objects remain undisturbed, yes, because the frequency of the glass is matches with the frequency of the note. And here I need to do this one like that. And here is, I want to show what happened when the wave, yes, when the external frequency matches with the frequency of the object. What happened is the wave is transferred efficiently. I want here to say the wave is an energy. Yes, the wave is an energy that is traveling in a medium. Then that wave is transferred efficiently, and what happens is if the object if the molecules of the object has a lot of energy, then what is going to happen is, in case of the crystal, in case of the glass, is going to break. Yes, and let's see. I need to do that. And here is frequency matches with the external frequency. It's a lot of energy and then breaks, as this is happening. And let's go back to the presentation. Also, resonance happened in the tuning fork. Then what happened is we had two tuning forks that had the same frequency. Then we can struck this tuning fork, and this tuning fork start vibrating. We don't touch this. We don't need to touch this one. Just this start vibrating because they had the same. This frequency of this sound matches with the natural frequency or the resonant frequency of the second tuning fork. Again, in this case, what is happening is the energy is transferred very efficiently. Yes. And here I want to show this video. And this way you remember why how the resonance happens. Yes. In this case, we had two tuning forks with the same frequency. Yes, the natural frequency matches. Then this star vibrating without touching, yes, without touching. And this same happened with the second one. That phenomenon is called the resonance. But the frequency must match, yes. Otherwise, this doesn't happen. Now, what they are doing is they are changing the frequency of the sound, yes. Because they change now, the frequency doesn't match. What is going to happen is the resonance phenomenon doesn't occur, yes, because the frequency in this case doesn't match. Let's move to the next slide. Now the last part I want to discuss is the intensity, and we will focus on the intensity of the sound. To discuss intensity, let's first remember, I want to remind you remember the definition of the power. Power is, maybe I will write here, power equals how much work can do in a unit time. Is the ratio work and time. But we know work is directly related with the energy. This is why work and energy, they have the same units. Then work, we can also define the power as energy divided by time. Is how much energy per unit time can transfer something, how much energy per unit time. Or we can say also is the rate of energy, the rate of energy. Then what is the intensity of the sound? The intensity of the sound is how much rate of energy can pass through unit area if the waves are perpendicular to this area. Right? The wave must be perpendicular to this area. Then the intensity is what is the rate of energy of the wave can pass through this area. And this is why we had here the intensity is power divided by area. Let's check the units. The units for power is joules per second, and we know it's watt. Then the intensity of the sound is power, which is watts, divided by the area units, which are meters squared. Then the units for intensity, and let me write here, the units for intensity will be watts per meter squared. Watts per meter squared. Then the intensity of the sound wave is the rate of energy, transferred to an area perpendicular to the waves. Transfer how much rate of energy passed through this area or is transferred in some area. And we can see also now, if we just the line test, we can see the relation between intensity and area is inverse relation. Larger area, less intensity. Larger area, less intensity. Here, this is why here, if the area is increases, the intensity is decreases. This is why someone is sitting here, they can hear the intensity of the sounds he can hear is less because the area is increases. The area is increases. And just to summarize, the power is the rate of energy is transferred by a wave. And the sound intensity is the power per unit area carried by the wave. And here I want to emphasize the wave transfer energy. what the wave is transferred is energy, because this is how the molecules can start vibrating, as is because the wave is transferred energy. I say the molecules of the medium is in which the wave is traveling. Here in this, we already discussed part of this graph, as we had here frequency and in the x-axis, and in the y-axis we had intensity. Intensity is watts per meter square. This is the same thing, just they wrote in this way, but this is the same if we had. Yes, is the units, is the intensity units. Then we discussed this is the frequency range in which the humans can hear sound. It's 20 hertz and 20 kilohertz, or 20,000 hertz. Yes. Below this frequency we cannot hear that sounds. Above this we cannot hear the sounds with the larger frequency. Yes, with larger frequency, with larger than 20 kilohertz. And we discussed this one before, but today I want to discuss the intensity. Yes, the intensity. Then these are the intensities. When we calculate the intensities, we had these values, yes, of the intensity. But what happened is, this part of the intensity is we cannot really hear anything. The part we can hear in the normal is when the frequency is 10 to the power minus 10, 10 to the power minus 8. This is the normal sound. It's my voice, is the intensity of my voice right now. But if we increase here, we have loud, yes, it's loud sound, and here this start become danger, yes, and here really is not good to hear that sounds, can damage our ears. Then this is about 1 watts per meter square. What happened is these scales are power of 10. We have minus 12, minus 10. It's more complicated numbers. Then the scientists, they design a new scale for us, for humans, is in decibel units. Then we are not going to go in detail with that, but you see here there is 12 order of magnitude. Here we had 0 to 120. Yes, is power of is going by 10, but the same number of order of magnitude we had here. And then is we can tolerate on sound is if the intensity of the sound is about 100 decibel, but about 100 decibel, you see it's become danger. Yes, and here is harmful. Yes, is about 100, about 90, 100. Then it's not good when the intensity of the sound is more than 100. Then here is the different in decibels scale. This part is quiet. We had normal sound in this region. We had loud here. This is start become danger. Yes, this sound, this intensity, if the intensity of the sound is in this region, and here is really is not good. Yes, it's harmful. Here we had few examples where the sound has this intensity. The intensity of the sound means the loudness. Yes, the intensity in case of the sound is related to the loudness of the sound. Then the loudness of the sound depends on the amplitude of the sound wave. Yes, if we have this, if the sound wave is, if the amplitude of the sound wave is small, then we have quiet sound. But if the amplitude is high, is increased, we have louder sound. Yes. Again, the intensity of the sound is related to the loudness, and the and the loudness of the sound or the intensity of the sound is related to the amplitude of the sound wave. Small amplitude, quiet sound, louder sound has more amplitude. And here another concept we already say is the loudness of the sound is related to the amplitude. Yes, amplitude. Yes, but also there is another quality of the sound is related to the frequency, and it corresponds to the pitch. Then higher frequency corresponds to greater pitch, and lesser frequency corresponds to lesser pitch. Yes, here we have more frequency. Yes, more frequency is more cycles per in the same time. Yes, this is more frequency. Then we had, in this case, we had greater pitch, less frequency, less cycle per time. Here we can say here we have time. Yes. This is time. It's not there, but it's time. Then we had here lesser frequency, lesser pitch. And just to summarize, in this case, we had low pitch and we had high pitch. Less frequency, higher frequency. Yes. And one important thing we can review here with the lower frequency and wavelength, they are inverse. Yes. Then low frequency, larger wavelength. Yes. More frequency, small wavelength. Yes, small wavelength. Remember, frequency and wavelength, they are inverse proportional. And in this case, if we had these two different kind of waves, we can see what we can say is, and these waves correspond to the sound, and we can say is the loudness is the same. Why? Because the amplitude is the same. However, the pitch is not the same. We had lower pitch in this case. Why? Because we had lower frequency. And in this case, we had higher pitch. Why? Because we had higher frequency. Yes, higher frequency. But however, the intensity means the loudness is the same because the amplitude of the waves are the same. Now is the last thing we want to discuss is the Doppler effect. And this effect occurs when a moving source of sound or a moving sound of a moving observer experiences an apparent change of frequency. Means we had here, this is the sound, this corresponds to the source of sound here in this part. This can be anything. Yes, can be microphone, can be the ambulance, can be the police car. It can be any sound, any source of sound. And here is the observer. And in this situation, the source of sound and the observers, they are not moving. They are at rest. And what happened with this? What is the situation? And this represents how this observer perceive the sound. And in this way we can see is the wavelengths are the same. Yes, the wavelength, you see the wavelength is the same, doesn't change. Now what happens is if the source of sound start moving, then what the observer is going to perceive is some change, some shift of frequency. And in this case, what happens is the observer will perceive, it's not good, but is the wavelength is decreases. Yes, the wave. And what happens is if the wavelength decreases, will perceive higher frequency. Yes, Remember, wavelength and frequency, they are inverse. Yes. If the wavelength decreases, the frequency will be increases. Then the observer will be perceive at the sound at higher frequency. Then what happens is when the source move, the observer will be receive wavelengths that are shortened, as they are small. But what happens if we had another observer to the right? Then that person will perceive higher, larger wavelength. Yes, it's not good, but it's this larger wavelength. Yes, and here the only the source of sound is moving. Yes, then this observer, if the source of sound is moving in this direction, then this observer will perceive the wavelength is small, but in this case, this will perceive larger frequency, yes, larger wavelength. Sorry. Here is just is the animation. This is the V. Yes, this is a V. This is the source of sound. And what happened? And this is in this case, this is the observer. And what happened if the source of sound is moving close and is moving away from the observer? Yes, or this microphone from the, let's call this one observer. Then this is going to happen as the wavelength is going to reduce, but is moving away, the wavelength is going to increase. Again, if the wavelength is decreases, then what happened? The frequency is going to increase. Yes. Then this is the animation. We cannot see this one, but what we will perceive, yes, sound when the source of sound is moving toward us. Yes, we are going to perceive is the frequency of the sound is going to increase. Yes, and this is happening with the ambulance is moving closer to us. We perceive frequency sounds at higher frequency. In this slide, we can summarize what is the Doppler effect in the sound wave. If the observer and the source of sound are at rest, if they are not moving, there is no change. There is no change in the wavelength. Yes, there is no change. There is no change in frequency of the sound. But what happens if the source of sound is approaches toward to the observer? The observer will perceive that the wavelength is decreasing and the frequency increases. If the source of sound moves away, yes, the other direction, the observer perceives that the wavelength increases, yes, increases, and the frequency decreases. And this is the idea of the Doppler effect. Yes, this is the idea of the Doppler effect. And we finish for today. Please try to complete all the assignments, the 2 assignments we had for this week, and stay safe. Bye bye.